Let's go through another example of conjugate acid and base pairs in Bronsted-Lowry acid and bases, and we'll also talk about the idea of the relative strength of conjugates as well. So we'll go through a bunch of things in this recap video. So I have an equation here, HNO2 plus H2O produces H3O and then NO2 minus. So the first thing I'm going to try to do in this problem is to identify what is my acid, what is my base, and then what are my conjugates. So the best strategy to do this is to look at each chemical species you have and figure out what happened to it. So remember that if it's all of these scenarios are, again, that we're looking at Bronsted-Lowry definitions. Remember that acid and base definitions, they can differ. So there's the Arrhenius definition, which we also use in this course, not in this example though. Arrhenius definitions apply more to stronger acids and bases that dissociate completely. And there's a third definition called a Lewis acid and Lewis base, which refer to electron donation and accepting. So that we're not going to look at so much in this course, but I would highly recommend you read up on them if you have time, because they will come into your studies for next year in university. Okay, so I know I'm dealing with the Bronsted-Lowry definition in this case. So this first chemical I've underlined, I want to just look at what happened to it. So when I do this, I actually need to look at both sides of the equation. So from the left side to the right side, what I've noticed is here's the counterpart on the right side. From left to right, HNO2 became NO2 minus. I know that it lost a hydrogen. Now hydrogen, remember, H plus is the same thing as a proton. So if I say hydrogen or proton, they mean the same thing. So if this lost a proton to become NO2 minus, I know by definition this is an acid. This is a Bronsted-Lowry acid, something that has donated a proton, or it's lost a proton, or it's lost a hydrogen in H plus ion. Okay, by definition, whatever happened to my Bronsted-Lowry acid, the product of the Bronsted-Lowry acid, the product is this guy, this NO2, this is the nitrite ion. The product is what I call my conjugate base. Okay, so the product is always going to be the opposite. So if it was an acid, it becomes a conjugate base. The reason being, this conjugate base can now accept hydrogens. It doesn't have any more hydrogens to donate, so it's not an acid anymore. It becomes a conjugate base. Okay, so where did my let's go back to the left side of the equation. Where did this hydrogen go? All right, so this hydrogen here that got donated, where did it go? Well, if we look at the whole equation carefully, it got picked up by the water. So if you look carefully, the water picked up a hydrogen to become H3O, the hydronium ion. So water, because it's picking up a hydrogen, it's accepting a proton or an H plus ion, I call this a Bronsted-Lowry base. And the product of my base, so this guy, H3O, this hydronium, this is what forms when my base picks up the hydrogen, it forms H3O. So I call this my conjugate acid. Okay, so the product of a base is a conjugate acid. And I know it's an acid because it's going to donate. It's going to have the tendency, H3O will donate an H. It can't pick up any more H's. There's no such thing as H4O. So it becomes a conjugate acid. Okay, so we've identified our 4 chemical species. And in class, we did something like this as well to bracket what belongs to what. Okay, just again, the visual, you want to look at all sides. It's not too difficult once you visualize everything. But I also want to quickly talk about the relative strength. Now, this HNO2, I'm just going to use more different colors to highlight. Okay, I know it's getting congested with colors, but this will hopefully help you visualize a little bit. So this guy over here, HNO2, this is a weak acid. I know it's a weak acid because we had talked about it in class about what are the 6 strong acids. Plus, I know, just looking at this equation, it forms an equilibrium, so I know it's not dissociating 100%. I know that it is a weak acid. This is actually, if you remember acid nomenclature, this is called nitrous acid, HNO2. Nitric would be HNO3. That's the base polyatomic, and this is one less oxygen. And here's the thing with its conjugate. So I'm going to highlight it in purple. Its conjugate base here is going to be stronger, or it's strong. Stronger. And its actual, this is a Bronsted-Lowry acid. The acid here is weak. This is a weak acid. So the rule is, if I have a weak acid, it forms a strong conjugate base. If I have a strong acid, if I had something like nitric acid, so HNO3 is strong, it would form a weaker conjugate base. Okay, now this becomes really important later when we get into more equilibrium problems and ice tables with Bronsted-Lowry acids and bases. So keep this in mind for now, okay? So the strength of my initial acid, if it's weak, it will form a strong conjugate and vice versa. Now, how do we know this? Basically, this was determined by chemists over the many years that experiments have been done. Chemists have formed data and they've ranked acids and bases according to their relative strength. And you have a data table that summarizes this in one of your notes. Okay, so again, keep that in mind for future problems. Now let's look at one more thing. So just to expand on this question slightly, let's look at this NO2 ion and see what happens when you, let's put it in another equation. So let's react this with water. Now you try to fill in the right side of the equation here. Okay, so you first of all predict your products, and then determine from this new equation what your acids and bases are, as well as your conjugates. So pause the video, take a second to do that. Okay, so hopefully you tried it, but I will take up the answer now. So if I'm predicting the products, I know that one of these chemical species will accept a hydrogen, one of them will donate a hydrogen. Well, if I look at this species over here, the NO2, it cannot donate a hydrogen. There aren't any. So I know that NO2 is my H acceptor. So, and by the way, we said that up here that it's a base. Okay, so we know that this is a base, but in this equation, if I'm starting this as a brand new reaction, I will call NO2 my Bronsted-Lowry base. It's going to accept hydrogen. The water is going to, now this is the only source of hydrogen in this equation, so I know that the water is going to donate a hydrogen, so I'm going to call the water in this example is the acid, the Bronsted-Lowry acid. So what this is going to look like on the other side is like this. So here we go. If I have, this is going to donate one hydrogen over here. This is going to give me HNO2. So this gives me the same thing I had above, this nitrous acid. So this is aqueous. Plus, now the H2O, it lost a hydrogen. So this gives me the hydroxide ion, OH, aqueous. And again, we can identify our conjugates. So because the HNO2, this is the product of this, of NO2. This is my conjugate acid. And then the OH is my conjugate base. It goes with the water. Okay, and this is again, and this reaction sort of blends two acid and base definitions together. If you think about it, this example sort of gives you an idea of also the Arrhenius in some ways actually. Arrhenius, because if I'm calling NO2 a base, not only is it a proton acceptor, but it also produced hydroxide from the water. And so this is a little confusing, but it sort of blends two definitions together. It's producing hydroxide, hence its basic nature, but it's also accepting hydrogen from a Bronsted-Lowry perspective. So acids and bases, they can be pretty confusing. There's a lot of little sort of nitty-gritty details, but hopefully with practice, again, you can look at all aspects of the equation, you can identify and practice, and it won't be so bad. But each skill builds into the next, so it's really important that you try to get a good grasp on this concept before we move on to the next one.